Welcome! In this session, we'll tackle LeetCode problem number 1909, remove one element to make the array strictly increasing. This is a fascinating problem that challenges your ability to analyze array properties and think critically about edge cases. Let's dive right in. In this problem, you are given an integer array called nums, and your task is to determine if the array can be made strictly increasing by removing at most one element. Now, an array is considered strictly increasing if every element is smaller than the one that follows it. In other words, for any index I, the condition nums I plus 1 must hold true. To solve this problem, you'll return true if it's possible to achieve this by removing one element, and false otherwise. The input consists of an integer array nums with a size between 2 and 100,000, where each element can range from -100,000 to 100,000. The output is a Boolean value that indicates whether or not the array can be adjusted to meet the strictly increasing condition. Let's look at a few examples to clarify the problem. In the first example, the input array is 1, 2, 10, 5, 7. Here, if we remove the element 10, the resulting array becomes 1, 2, 5, 7. This new array is strictly increasing because each element is smaller than the one that follows it. Since we were able to make the array meet the condition by removing just one element, the output is true. Now consider the second example, where the input is 2, 3, 1, 2. In this case, no single element can be removed to make the array strictly increasing. For instance, removing 3 results in 2, 1, 2, which is not strictly increasing, and removing 1 results in 2, 3, 2, which also fails the condition. Therefore, the output here is false. In the third example, the input array is 1, 1, 1. This array contains repeated values, and no matter which single element you remove, the remaining array will still contain duplicates. For example, removing any 1 still leaves 1, 1, which is not strictly increasing. Hence, the output in this case is false. Finally, consider the input 1, 2, 3. This array is already strictly increasing because every element is smaller than the one that follows it. Since no removal is needed, the output is true. To summarize the constraints and edge cases, the length of the array must be between 2 and 100,000, and each element can range from -100,000 to 100,000. Some key edge cases to consider include arrays with the minimum size of 2 elements, such as 1, 2, or 2, 1. For these arrays, removing one element will always leave a single element, which is trivially strictly increasing. Arrays that are already strictly increasing, like 1, 2, 3, 4, should immediately return true without requiring any changes. On the other hand, arrays where all elements are identical, such as 5, 5, 5, cannot be made strictly increasing, even with one removal. Another important edge case involves large arrays, specifically those with the maximum size constraint of 100,000 elements. For such cases, it's crucial that the solution is efficient and can handle the input within a reasonable time frame. The algorithm needs to ensure that performance does not degrade significantly as the input size approaches the upper limit. Taking these constraints and edge cases into account will help you design a robust solution to determine whether the array can be adjusted to meet the strictly increasing condition. To solve the problem, we need to determine if we can make the array strictly increasing by removing at most one element. The brute force approach is a straightforward way to tackle this. The idea is simple: for each element in the array, simulate its removal, then check if the remaining array is strictly increasing. This involves looping through each index, creating a new array without the element at that index, and verifying the condition that every element is less than the next. If we find even one valid array that satisfies this, we return true. Otherwise, after testing every possible removal, we return false. While this approach is intuitive and easy to implement, its time complexity is quadratic because for each of the n elements, we perform a linear check on the remaining array. This makes it unsuitable for large arrays, especially when n is in the range of tens or hundreds of thousands. Additionally, it requires extra space to create a new array for each removal, which can be an overhead for very large inputs. The brute force approach, while simple, has a major drawback: it is inefficient for large arrays due to its n² time complexity. To address this, we can use an optimized approach that focuses on identifying the first violation of the strictly increasing property. This happens when we find an index I where nums I is greater than or equal to nums I plus 1. Once we detect this issue, we analyze whether removing one of the two problematic elements, either nums I or nums I plus 1, can resolve the situation. Specifically, we perform localized checks. If we remove nums I, we verify whether nums I1 is less than nums I plus 1, provided that I is not the first index. Alternatively, if we remove nums I plus 1, we check if nums I is less than nums I plus 2, assuming nums I plus 2 exists. If either of these removals restores the strictly increasing order, we return true. Otherwise, we return false. The key insight here is that in a valid solution, at most one violation can exist. By focusing on this single problematic region, we eliminate the need for redundant checks across the entire array and achieve significant efficiency gains. The complexity of the optimized approach is a significant improvement over brute force. It operates in O(n) time because we only traverse the array once, and the checks for resolving the violation are constant time operations. Additionally, the space complexity is O(1), as we perform all operations in place without requiring additional data structures. This makes the optimized approach highly efficient in terms of both time and space. Now, why do we choose this approach as the preferred strategy? First, it is the most efficient for large inputs, with linear time complexity compared to the quadratic time complexity of the brute force method. Second, it avoids unnecessary computations by focusing solely on the problematic indices, leveraging the fact that only one removal is allowed. The implementation is straightforward and does not require any extra memory, making it ideal for scenarios where performance and scalability are critical. While it does require careful handling of edge cases, such as very small arrays or adjacent violations, these can be managed effectively with thoughtful coding. In conclusion, the optimized approach is the superior choice for solving this problem. It offers a perfect balance of efficiency, clarity, and scalability. With its linear time complexity, constant space usage, and focus on minimizing redundant computations, it is well suited for both competitive programming and real-world applications. Although the brute force method is conceptually simpler, its inefficiency for large inputs makes it impractical. The optimized approach, while slightly more complex, is robust and handles edge cases effectively. Ultimately, it provides a clean and scalable solution to the problem, ensuring optimal performance even for the largest arrays. To solve this problem, we need to determine if an integer array can become strictly increasing by removing no more than one element. A strictly increasing array means that for every index I, the condition I plus 1 must hold true. To achieve this, the algorithm starts by identifying any violations of this property. We traverse the array from left to right and look for the first instance where I equals I plus 1. For example, in the array 1, 3, 2, 4, we find a violation at index 1 because 3 is not less than 2. If no violations are found during the traversal, the array is already strictly increasing, and we can immediately return true. Otherwise, we move on to evaluating two possible cases to fix the violation. First, we consider removing the current element causing the violation, I, and check if the remaining array becomes valid. Specifically, we ensure that I1, I plus 1 if I0. Alternatively, we consider removing the next element, I plus 1, and verify if I plus 2, if I plus 2 is within bounds. These two scenarios allow us to test whether we can resolve the violation while maintaining the strictly increasing property. Special attention is given to edge cases, such as when the violation occurs at the beginning of the array, where only the elements from index 1 onward need to be checked. If the violation occurs at the end of the array, specifically at index n2, we only need to verify the array up to n2. This simplifies the checks since the removal of an element near the boundaries has fewer constraints to consider. After evaluating both removal scenarios, if neither resolves the violation, we return false because the array cannot be made strictly increasing by removing just one element. On the other hand, if either case successfully fixes the violation, we return true. The key insights for this algorithm are as follows. First, we only need to focus on the first violation because the problem guarantees that removing at most one element will suffice. Second, by evaluating both removal scenarios, removing I or I plus 1, we ensure that all possible ways to fix the array are covered. Lastly, the algorithm is efficient, as it only requires a single traversal of the array to find the violation, and the checks for each case are performed in constant time. This gives our solution a time complexity of O(n). Regarding data structures, the algorithm is straightforward because it only uses the input array itself and simple index tracking to locate and handle violations, making the space complexity O(1). The space complexity of this solution remains O(1), because no additional data structures are used. Now let's look at the pseudocode to solidify our understanding. The function starts by initializing a variable found_violation as false to track whether a violation has been encountered. We then iterate over the array with a loop that checks if nums I equals nums I plus 1. When such a violation is found, we first check if a violation has already occurred before. If it has, then the array cannot be fixed by removing just one element, so we return false. Otherwise, we mark found_violation as true and proceed to evaluate the two cases. For the first case, we check if removing nums I ensures the array remains valid. This is done by comparing nums I1 with nums I plus 1 if I greater than 0. If this condition fails, we move to the second case, where we check if removing nums I plus 1 satisfies the condition nums I plus 2, provided I plus 2 is within bounds. If both cases fail, we return false. If we complete the loop without returning false, it means the violation was successfully fixed, and we return true to indicate that the array can be made strictly increasing. Let's apply the algorithm to a few examples. For the input 1, 3, 2, 4, the first violation occurs at index 1 where 3 is not less than 2. In case 1, removing 3 leaves 1, 2, 4, which is strictly increasing. In case 2, removing 2 results in 1, 3, 4, which is also valid. Since at least one of the cases works, we return true. For the input 1, 2, 5, 3, 4, the violation occurs at index 2 because 5 is not less than 3. In case 1, removing 5 leaves 1, 2, 3, 4, which is valid. In case 2, removing 3 results in 1, 2, 5, 4, which is not strictly increasing. Since one case works, we return true. For the input 1, 2, 3, 4, 5, there are no violations, so we return true immediately. Finally, for the input 5, 4, 3, 2, 1, the first violation occurs at index 0. Neither removing 5 nor removing 4 results in a strictly increasing array, so we return false. These examples demonstrate how the algorithm efficiently handles various scenarios to determine the result. In this solution, the goal is to determine if an array can be made strictly increasing by removing at most one element. To achieve this, we define a helper function as strictly increasing, which checks if a given list satisfies the condition I plus 1, for all valid indices. This function iterates through the array and returns false if it encounters any violation, otherwise, it returns true. The main function, can be increasing, iterates over all indices of the input array nums. At each iteration, it removes the element at the current index and creates a new array, new_nums. It then checks if this modified array is strictly increasing using the isStrictlyIncreasing function. If any such removal results in a strictly increasing array, the function immediately returns true. If no single removal satisfies the condition, the function returns false, indicating that the array cannot be made strictly increasing even after removing one element. This implementation is efficient for small input sizes, as it leverages a helper function and simple iteration. In this Java implementation, we start by defining a class called solution and a method named canBeIncreasing, which takes an integer array, nums, as input. To help us determine if an array is strictly increasing, we first define a helper method called isStrictlyIncreasing. This method iterates through the array using a simple for loop and checks if each element is less than the next one. If any element violates this condition, the method immediately returns false. Otherwise, if all elements satisfy the condition, it returns true. Next, we move on to the main part of the algorithm, where we iterate through the nums array to test the removal of each element one by one. For every index, we create a new array, new nums, by skipping the current element. This is achieved using a nested loop where we copy all elements except the one at the current index into the new array. Once we have constructed the new array, nums, we use the isStrictlyIncreasing helper method to check if this modified array satisfies the condition of being strictly increasing. If it does, we return true immediately, as removing this single element makes the array valid. The loop continues testing each index in the nums array. If, after trying to remove every element, no valid strictly increasing array can be formed, the method ultimately returns false. This ensures that the solution comprehensively evaluates all possibilities and only returns true if at least one valid configuration is found. In this example, we start with the array nums equal to 1, 2, 10, 5, 7. The goal is to determine if removing just one element can make the array strictly increasing, meaning each number must be strictly greater than the one before it. First, we remove the element at index 0, which is 1, resulting in the array 2, 10, 5, 7. We then use the helper function isStrictlyIncreasing to verify if this new array satisfies the condition. Comparing 2 and 10, we find 2 is less than 10, which is fine, but 10 is not less than 5. This makes the array not strictly increasing. Next, we remove the element at index 1, which is 2, resulting in 1, 10, 5, 7. Again, we check the condition. While 1 is less than 10, the comparison between 10 and 5 fails, so this array is also not strictly increasing. Now, for the third iteration, we remove the element at index 2, which is 10. This creates the array 1, 2, 5, 7. Using isStrictlyIncreasing, we compare consecutive elements. First, 1 is less than 2, which is true. Next, 2 is less than 5, and 5 is less than 7. All comparisons succeed, meaning this array is strictly increasing. Since we have found a way to make the array strictly increasing by removing just one element, we return true as the output for this example. In this second example, the input array nums is 2, 3, 1, 2. The objective remains the same: remove one element to make the array strictly increasing. Starting with the first iteration, we remove the element at index 0, which is 2, resulting in 3, 1, 2. Checking if this array is strictly increasing, we find that 3 is not less than 1, so the condition fails. Moving to the second iteration, we remove the element at index 1, which is 3, creating the array 2, 1, 2. Here, 2 is not less than 1, so this array is also not strictly increasing. For the third iteration, we now remove the element at index 2, which is 1, resulting in 2, 3, 2. Checking this array, 2 is less than 3, which is fine, but 3 is not less than 2, so this is not strictly increasing. Finally, in the fourth iteration, we remove the element at index 3, which is 2, creating the array 2, 3, 1. Comparing the elements, 2 is less than 3, but 3 is not less than 1. Since none of the iterations result in a strictly increasing array, we return false as the final output for this example. In this third example, the input array is 1, 2, 3, 4. This array is already strictly increasing, meaning each element is greater than the one before it. Removing any single element will still result in a strictly increasing array. For instance, in the first iteration, we remove the first element, 1, resulting in 2, 3, 4. Checking this array, 2 is less than 3, and 3 is less than 4, so it satisfies the condition. As we've already determined that removing one element can maintain the strictly increasing property, we immediately return true as the output. The key idea behind this solution is to iterate through the array, removing one element at a time, and checking if the remaining array is strictly increasing. This is accomplished using the helper function isStrictlyIncreasing, which validates the condition by comparing consecutive elements. If we find even one instance where removing an element makes the array strictly increasing, we return true. Otherwise, after all iterations, we return false. In terms of complexity, the time complexity is O(n) squared, because for each of the n elements removed, the helper function performs an O(n) check on the resulting subarray. The space complexity is O(n) due to the creation of a new array for each removal. In analyzing the time complexity of our solution, let's start with the outer loop. This for loop is designed to iterate over all elements of the array nums, which has n elements, meaning it will run exactly n times. For each iteration of this loop, we create a new subarray, new_nums, by concatenating two slices. The first slice, nums I, consists of elements before the current index I, and the second slice, nums I plus 1, includes elements after I. In Python, slicing an array requires time proportional to the size of the slice, so creating this new array takes n time, as the combined size of the slices is n1. Finally, we call the helper function is strictly increasing to verify if the subarray is strictly increasing. This function loops through all elements of the subarray, which has n1 elements, making its time complexity n. So, each iteration of the outer loop involves n, for creating the subarray and n, for the monotonicity check, leading to a total of n time per iteration. Now, when we consider the overall time complexity, the outer loop runs n times, and in each iteration, we perform operations that take n time. Therefore, the total time complexity is n multiplied by n, which simplifies to n squared. Moving on to space complexity, let's examine the subarray creation process. In each iteration, we create a new subarray new_nums of size n1, requiring n auxiliary memory. The is strictly increasing function, on the other hand, operates with O1 space since it uses only a small number of variables for comparisons and does not rely on recursion or additional data structures. As a result, the primary contributor to space usage is the auxiliary memory for the subarray, making the space complexity n. To summarize the overall space complexity, it is dominated by the storage of new_nums in each iteration. However, since only one instance of new_nums exists at any given time, the total auxiliary space required remains n. Now let's explore the best, average, and worst-case scenarios for this algorithm. In the best case, the array becomes strictly increasing after removing the first or second element, allowing the function to exit early. This reduces the time complexity to n, as only a small number of iterations are executed. In the average case, the function typically evaluates about half of the elements before finding a solution. Despite this, the n squared term still dominates. Finally, in the worst case, the array cannot be made strictly increasing by removing any single element, forcing all n iterations of the outer loop to execute. Here, the time complexity remains n squared. Comparing our solution to a brute force approach reveals significant optimization. A brute force method would generate every possible subarray of size n1 and check each for strict monotonicity. This requires n squared subarrays, and since verifying monotonicity for each subarray takes n time, the overall time complexity would balloon to n cubed. In contrast, our solution avoids explicitly generating all subarrays. Instead, it dynamically constructs the required subarray in n time during each outer loop iteration. This optimization reduces the total time complexity to n squared. To mathematically verify our big O analysis, the outer loop runs n times, and for each iteration, subarray creation and monotonicity checks together take n. Thus, the total time complexity is n times n, resulting in n squared. Similarly, the space complexity is determined by the largest subarray stored, which is n. Therefore, the algorithm is proven to have a time complexity of n squared, and a space complexity of n. One common mistake in this problem is neglecting edge cases, such as arrays with only one or two elements. These scenarios are straightforward because any array of size 1 or 2 is inherently strictly increasing after removing at most one element. Another frequent error is removing the wrong element. It's tempting to assume that the element causing the first violation of the strictly increasing condition is the one to remove, but this isn't always correct. Sometimes, removing the element before the violation leads to a valid sequence instead. Additionally, failing to reset comparisons properly when checking subsequences can lead to errors in your logic, producing incorrect results. Inefficiency is another pitfall. Using nested loops to try all potential subarrays results in quadratic time complexity, which is unsuitable for the input size constraints of this problem. Lastly, some misunderstand the problem's requirement for strict inequality, allowing sequences like 1, 2, 2, which are actually invalid. Always ensure that the condition I plus 1 is strictly enforced. A key insight for this problem is that it can often be solved in linear time by scanning the array and identifying at most one violation of the strictly increasing condition. Once you find a violation, you can validate the sequence by checking the result of removing either the current element or the one immediately before it. This efficient approach is crucial to solving the problem within the constraints. Another useful perspective is recognizing that this problem is part of a broader category of single-edit problems, those where you're allowed to make one modification, such as removing, replacing, or inserting an element, to meet a condition. Identifying this pattern can help you draw parallels to similar problems and derive efficient strategies. In interviews, it's important to communicate trade-offs. If you initially propose a brute force solution, acknowledge its inefficiency, and explain how you'd optimize it. This shows critical thinking and an understanding of algorithm design. Finally, always test your logic thoroughly with edge cases, such as arrays with duplicates, arrays that are already strictly increasing, or those with exactly one downward violation. This problem has connections to several related problems that can help you deepen your understanding. For example, LeetCode 665, non-decreasing array, asks you to modify at most one element to make the array non-decreasing, which is conceptually similar but focuses on a different inequality. LeetCode 674, longest continuous increasing subsequence, challenges you to find the longest strictly increasing contiguous subarray, which emphasizes subsequence length rather than element removal. Another related problem is LeetCode 978, longest turbulent subarray, which explores alternating patterns of increasing and decreasing elements. Lastly, LeetCode 300, longest increasing subsequence, involves finding the length of the longest increasing subsequence, not necessarily contiguous. These problems share overlapping techniques and insights, so exploring them can strengthen your problem-solving skills in handling sequences and array manipulations. There are multiple approaches to solving this problem, each with its pros and cons. A brute force approach involves removing each element one by one and checking whether the resulting array is strictly increasing. While this method is easy to understand, its O(n)² time complexity makes it impractical for large inputs. A more efficient solution is the greedy approach, which works in O(n) time. Here, you traverse the array while keeping track of the first violation of the strictly increasing condition. At most, you need to validate two scenarios, removing the violating element or the one immediately before it. This approach is optimal and handles large input sizes effectively. Another variation that can be useful in certain scenarios is the two-pointer technique. With 2 pointers, you can validate subarrays or ranges when a violation is detected, which is particularly helpful in problems that focus on subarray or range-based checks. These alternative methods provide a spectrum of strategies, from simple to efficient, depending on the context and constraints of the problem. Great job! We've now explored the solution to LeetCode problem number 1909. Remember, solving array problems like this strengthens your problem-solving skills and prepares you for real-world scenarios. Thanks for joining, and see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!